Okay, so today we are going to solve the question counting numbers. Your task is to count the number of integers between a and b where no two adjacent digits are the same. Okay, and a and b can be up to the 10 to the power 18. Okay, so that's the question. So what is our question? We are given two numbers a and b. We have to count how many numbers are there in between them, including a and b. So how many numbers lies in this array which has no two adjacent digits same. No two adjacent digits should be same. Okay, so no two adjacent digits should be same means like the 5 5 this, suppose this is the number, so this violates the condition because this 5 and 5 are same numbers and they are adjacent, so these numbers would not be counted. So we have to find out what are the 3 5 6 8. Okay, so this is a valid number, so we have to find out how many valid numbers which satisfies this condition lies between the range a and b. Now here the simple brute force will not work because a and b are 10 to the power 18. So if we look from a to b, it can go up to maximum 10 to the power 18. So this will give us really okay. So what would be the best course of action here? So this question is basically the basic of digit DP. This question is a question of digit DP. I mean, if you know how to solve this, then only you can solve this. Okay. So this question comes under the concept of digit DP. So to tackle this type of questions, there was a concept of digit DP. Okay. So what it shows? Okay. So it shows that if we can't iterate through to every number, okay, let's see digit by digit. Okay. So let's see. For a digit, a number can be represented in form of digits. Like if a number is 9998, so it can be represented with four digits 999 and 8. Okay. So let's see in terms of digit. So number can be maximum 10 to the power 18. So the digits can be up to the 18. So n can be maximum 18. Okay. So now this is something that we can work on. So actually n would be maximum 19. Okay, so now we can work on something like this. Okay, suppose we have 10 digit number. Let's say the number was, let's suppose, okay, one more thing. We have to find out A to B. Now it would be easier for me to find out 0 to B because now I only have to look for conditions for B. Now if I know the answer for 0 to A minus 1, then this problem is same as this, just the B value got, the value for B is different. Okay, so I can solve these two problem individually, and what I will do, I will do the answer of this minus answer of this. Okay, so this would be my final result. Okay, why I did this? Because it would be easier to maintain just one variable than to maintain two variables. Okay, and the problems are basically the same. Okay, so now let's look how we can find from 0 to B. Okay, so I want numbers smaller than B. Okay, so let's suppose the B was 9987. Okay, 9187. Okay, suppose this was P. So now we will try to create all the numbers which are less than this. So what are the values I can put here? Okay, so I can put 1, I can put 0 here. Okay, I can put 1 here. I can put 2 here. Up till I can put 9 here. Okay, so let's see if I put 0 here. So now if you see, no, let's suppose, what if I put 1 here? Okay, So now you will see that now as this is one, no matter which digit I put here, every digit is valid. Every digit is valid. Okay. So if I put anything which is less than 9, I can put 1, 2, 0 up to 8. If I put any number less than 9, then now whatever value I put here, it would be less than this number only. So now the only condition I have to look for is the previous element. Okay. So uh, why I am going by this method? Because iterating through every digit is not feasible. So what we are doing, we are building our number digit by digit. And by building our number digit by digit, what we will find out? We will find out that uh, what are the all the possible numbers. So we by looking at digit by digit, what we are eliminating, we now just have to look for the number of digits, that is n. Okay, so now we have to iterate n times. Now for each digit, what I'm checking what are the possible values I can put here. Okay, so if we are starting, so if the number is, let's say, 9187, so I can put anything here from 0 to 9. So if I put 1 here, then I can put 0 to 9 any number. Okay, because now as I have put on a smaller number earlier, so now what number I put, this whole number would be smaller than this only. Okay, so what are we currently tracking? Okay, we are tracking at which index we are. Okay, the second thing we are tracking is previous number. Why we are tracking this? Because in question we have to find out no two adjacent digits are here. So if I put 1 here, then I can put any number here except 1, because then this condition would be false. So let's suppose I put 2 here. Okay. So now here also I can put any number. Okay. So let's put 5 here. Here also I can put any number. So let's put 7 here. And here also I can put any number except 7. So let's put 6 here. Okay. So we have formed a number. Now if we go again plus 1, then we have ended our spaces. So now, then we can return plus 1. That is, we have found one number. Okay. So what this what would be the answer to what would be the answer of this? So it will store every possible what would let me so if we are index 1, if we know the answer for every number which are 4 digits number which we can put here, so then we answer then we can say that okay, so if we are starting from 1, what are the all the numbers I can put here. Okay, so that's how we are calculating. So what we needed till now, we needed the index. We also needed the previous index. Okay, because we can't put the same index twice, or we can't use the same number twice, same digit twice. Okay, so now here comes the third condition, that is tight. So what this tight shows, it shows whether we are bound by the upper limit or not. What do I mean by that? Let's suppose the first number I put was 9. Okay, initially the B was 9187. Now, if I put 9, then I am in my tight bound. Tight bound means that I am in my, now I can't put anything here. Okay, I can put maximum 1 only, because if I put 2 here, then it would be bigger than this number. Okay, so this tight shows that whether I am bound by the condition, whether I am bound by the digit of number B or not. So if tight is 1, that means I am bound by the limit of this digit. So now the maximum I can go is 1. Now if I put 0 here, then again my tight would be 0. Now I can put anything, because no matter what I put here, it would be less than this number only. But if I am again putting 1, then my tight again would be 1, because now I am again bounded by my number, so I can go from 0 to 8 only. So till now what we are storing? I, previous, and tight. Okay, so this with these three condition, we can create all the numbers. Okay, so what this will give me? Okay, so with these three numbers, I can find every possible number. So what I will do, so if I is, we will start from I equal to 0. Previous state would be, let's say, -1. Okay, because previously we can, there is no digit, so we can put any number. And the type is 1 because we are in a tight condition. We can't go from any number to 0 to 9. We can maximum go to a tight. In this case, that is 9. If this was 8, then our tight would be, then we can go from 0 to 8. Okay, so uh, now is there anything missing, guys, or is this enough for us? Okay, you will understand this better when I will write code. But now let's look for more things if we are missing anything. Okay, so what if I, okay, what if this one? One is also a number. It satisfies 1 0. Let's say this is a number. So this 1 0 is a number. Okay, it satisfies our condition. It's less than b and it doesn't have a digit repeated. So this should be a value. But from this, we will never find this number because it will give false only when these two numbers are 0. Because if we are just checking the previous number, then 0 is equal to 0. So this would give us false. So this number would be never counted. So for this condition, we have to add again one condition, that is leading zeros. Okay, what this will give us? This will give us how many leading zeros are there in this number. Okay, so if the number of leading zeros is 3 and we are at index 4. So as you can see, if the number of leading zeros are 3 and we are at 4, so we can put here 0 because this is valid. So we haven't still started a number. Okay, but if the leading zeros is 2 and we are at 4, that means we can't, we have already put something here. Okay, so if this was the case and we are looking at this index, then we can't put 0 here. Okay, because leading zeros are just 2 and we are already at index 5. Okay, so if the number of leading zeros are less than the current index is 4 and our leading zeros are 3, then we can put a 0 here. Okay, so then we don't have to look for this condition, that is previous should be equal to, should not be equal to current. Okay, this can override because of this condition. Okay, so that's why we need one more variable for the sole exception of zeros. Okay, so now let's write an algo. So from this you will understand better. Okay, so what we are required the index which we are at currently. Okay, what is one more thing which we are required? We are required by the upper limit. Okay, let's say we already have these things. What we have? We have a upper limit b. We have a number b. Okay, now we will convert it to string first. Why we would do that? Because then it would be easier for us to iterate. Okay, so if it was a number, suppose it was a number in a number form, int form, then to extract every number, it would be difficult. But if we convert it into string, then we can directly extract any number with the help of, we can directly look into that number because it's a string. Okay, so we have converted b into string. Now what are the conditions we require? If we require the index, we require the previous, we require leading zeros, that simply says zeros, and we require tight. Okay, what is a tight? What would be our base condition? Base condition would be if I is less than and we would return 1. Okay, that means we have reached at the end, so we can create this number. Okay, so now let's create a lower bound. Lower bound would be 0 because we can go from 0 to 9. Okay, so by default, the upper bound would also be 9 because we can go till 9. Now, when will this upper bound be changed? It would be changed if tight is 1. That is, we are in a tight position because now we can't put anything freely. So if we are at tight, what we will do? We will change our we would change our upper bound to the based on the index. That is, whatever digit is at let's say the string was s. So whatever digit is in s of I minus 0. Okay, so now we are bound by this. Okay, so now we will simply iterate from from lower bound to upper bound. Here we would create first answer equal to 0. Okay, now answer plus equal to. Okay, so now what are the conditions? If let's say if leading zeros are present, first we would treat the condition for leading zeros. So if zeros are zeros plus 1 is equal to I. That means currently we haven't started the number yet. So now we can ignore the request. Now we can ignore for the tight. Now we can ignore the previous condition because the previous will be 0 only. Okay, so now we can put anything. So if this condition, then if the current number is also 0, then what we would do? We would pass on I plus 1. Okay, now the current number is 0. So previous would become 0. And because this is part of the leading zeros, so zeros plus 1. Zeros plus 1 and the tight would be same. Okay, because if we are at the tight, then the tight would be same only. No, actually, just a second. So for this, what we would check? If zeros plus 1 is equal to I. Okay, this means that our current index, we haven't started the number yet. So if this is the case, then what we would check? We would check that if the current number is 0, then what we would do? We would put answer plus equal to solve for next number. The previous would be 0, that is the current number. And the zeros would be zeros plus 1. And for the tight condition, what we would do? We would do that if the previous means if the position we currently are is tight, because there would be two conditions for tight. If we currently are at tight or if we currently are not at tight. If we currently are not at tight, then we can put anything. So this would be 0 only. Okay, but if we are tight, then if the number which we are looking is same as the number means upper bound, Means if we are at tight and if we are looking for that tight number, then only tight will 1. Otherwise, it would be 0. Because let's say upper bound was 3. And if we have put on 2, now the tight again become relaxed. So it would be 0. So that's why tight and what would be the second condition? That would be A should be equal to upper bound. Then only it would be 1. Otherwise, it would be 0. Okay. So this is a tight condition. Now if J is equal to 0, then this would be condition. Else simply J and zeros would not be plus 1. They would be as it is. Okay. And the tight condition here would be same only. I would not write this condition again and again. So I would just represent it with T. Okay. Now if this is not now if what if this was not the case? If this was not the case, then we can only add if previous is not equal to current number. Okay, so the previous and current number are not equal, then only we would add this number. Then only we would put this number. Okay, so the previous should become J, 0 should become as it is, and right condition would be follow. Okay, so this is just the okay. So now we are done. Okay, so this was our algo. So what we did, we have 4 states: the current index we are at, the previous digit, what are the number of leading zeros, and whether we are tight or relaxed. Okay, so what we will do, if we have completed our number, we would return 1. Okay, otherwise what we will do, we would first initialize our lower bound and upper bound to 0 or 9. Now if we are tight, means we are not relaxed, we have to look for greatest number. So we would change our upper bound with s of I minus 0. Okay, now we will initialize our answer by 0. Now from lower bound to upper bound, what we will see? If we will see that if we haven't started our number yet, that is 0 plus 1 equal to I. What this will show that we haven't started our number yet. So if we are currently at third index, okay, so 0 plus 1 would be I. Okay, so this means that we haven't currently started our number, so we can put 0 again here. Okay, so that's why this condition. Actually, it would be zeros only because here we are looking for uh, 0 base index. So when we are at 2th index, we check that how many zeros we have put on. If we have put on 2 zeros, then we can again put a 0 here. So if this is the condition and if the number is 0, then we would increase the number of zeros by 1. And if that is not the case, then we would simply put the number and zeros would become as it is. Now, if the if we have already started a number, then we have to look for the previous condition. So that's why now we have to put this condition. If previous is not equal to J, then only we have to increment the answer. Okay. So now we will memorize it with TP. So how many states we require? We require 4 states. Okay. So let's see. We required index. We required previous number. We also require leading zeros, and we also require tight condition. Okay, so how many index can there be? Maximum 19 index. Let's say 20. Okay, how many? What are the values of previous? It can go from 0 to 9 only. So it would be 10. What are the maximum number of zeros that we can have? That is 18. So let's say 20. And what can be the value of type? It can be either 0 or 1. So it is 2. So our total time complexity would be 19 20 into 20 into 10 into 2. Okay, so that would be 2228. It would be around 8,000. Okay, so this is far less than 10 to the power 8. So you our test case will be passed. Okay, so now let's code it. Okay, here it is better to code with this by recursion only, because here we are dealing with multiple states. So it's better to it would be better for us to write a recursion code instead of iterative code, because although iterative code would be better, but then it would we would have to run multiple loops. Like there are four loops: one for index, one for write, one for previous index also. So that's why it would become more complex and it would not be easy to understand. So that's why in digit TP problems we don't go for iterative code. We write the recursive code. I mean, there are people who are excellent in their work. So if you are practiced enough, you can also directly write the iterative code. But you will not get the questions. You will not get that many questions of this type of problem. So it is actually quite rare, and it's a bit advanced topic also. So that's why everyone writes the recursive code. Okay. Even me, I also not solved that many problems of this topic DGTP. So that's why that's code. Okay, what we have to do? Let's define. Okay, we would convert this into string. Okay, let's say string equal to string A, and string B would be string number B. So it would be A minus 1, because we are including the number A in this range. So that's why we would subtract this one. Okay, so now what would be our answer? Let's calculate for A. That would be answer 1 would be solve for A. And answer 2 would be solve for B. What we will do, we will simply subtract the answer. Okay, solve for B minus solve for A. Okay, now let's write another function. Solve, which would take string as input. So what we need here, we need a DP. Okay, so what are the max states of this DP? So it would be n can go till 20. What was our, let me write down the states here. TP of index. The next one would be previous zeros and right. So what does this index shows? Index shows current index at which we are at. Okay, previous shows the previous number which we have put. Zeros give me a number of leading zeros. And right gives me whether I am right or the text for my upper band. Okay, so the index can go till 20. The previous number can go till 0 to 9, so it would be 10. The zeros, the leading zeros can go till n, so that the 10 and right would be 0 or 1. Okay, so now let's set this tp to -1 size of tp. Now we would call the recursive function that would be calculate tp. We would start from 0. The previous number is -1. Okay, so leading zeros are 0 and right is 1, and we would return this one. Okay, so what are the values we have to pass along with this? One is the s, and the second one is RDP. Okay, so this would do. You can also pass n with it. Okay, so now let's write down this function. Index previous zeros, type string as and array tp. And size n. Okay, so what I said, if we have this data and that is if I is greater than equal to 1, we will return 0. Sorry, we will return 1. Okay, now if we already find out the answer previously, if we have found out the answer previously, that means if this value is not equal to 0, is not equal to -1, then simply we would return this previously stored number. Okay, so the here if previous is not equal to -1, because then this would give us out of bound error. Okay, so we have put a we have already put that in a condition earlier. Okay, so now what we would do, let's say our answer is 0. What would be our lower bound? It would be 0. What would be our upper bound? It would be 9. Now we are if we are right, so then it would be s of index -0. Otherwise it would be 9. Okay, so if we are not relaxed, then the number would be the index itself, otherwise it would be 9. So let's move towards I equal to 0, lower bound to upper bound. There is no need for this lower bound. Let's just see. Okay, as I said, if we are zeros. So we can directly add that in a condition. So if zeros is not equal to index, means if zeros are less than index, so that means we have already started a number, and then only we will look for a previous condition, that is previous is not equal to, if previous is equal to I, then we will continue, then we will not look for this number. Okay, because we can't put this number, so what we did, we put the zeros condition also here, because if zeros are less than the current index, that means we have already started our number. So now this condition have to be checked. If previous is equal to I, then we would continue. Okay. Otherwise, what we will do? We will do answer plus equal to. Now, what would be our index? It would index plus 1. The previous would be this number, that is I. Now, if zeros are equal to, we would only add plus 1 if zeros are equal to the current index. That means we have not currently started our number. So zeros are equal to index. And one more thing would be if the current number is 0. And if the current number is equal to 0. Okay, so if these two conditions are true, then it would give 1, and so that's why then we would add two zeros. Otherwise, it would be same only. Okay, now for tight and what should be the next condition for tight? If I is equal to upper bound, then only we are at tight. Okay, so next we'll just pass everything. Okay, so now we will return our answer. Before returning, we will store it in our TP. Index previous zeros and okay, now let's see 1, 2, 3, and 3, 2. Okay, so to pass array by reference, we also have to give its define. We have to give its size also. So that's why we have it. Instead, you can directly make it a global one. Okay, you can define a global DP here. So that will be a better way. But let it be as it is now. Okay, so let's try to submit it. Okay, so it gave me wrong answer. Well, let's see what can be the issue here. Okay, so it's a mistake. We have to define it in long. Okay, let's erase this. Would make it a global DP. because it's not a good practice to pass on DP as a pass on array as a reference. You can pass on vector as a reference, but it's never a good option to pass. You can pass vector as a reference, but it's never a good practice to pass array as a reference. So we will define globally and set DP. Now everything should be fine. Okay, so what we were actually using int. That's why it got integer overflow. Okay, so all test cases are passed. So we have solved this question. So this was a question of TGTP. So see you in the next video, guys.